Assalamu alaikum everyone. So today we are going to start uh, past papers for the ETPs, and it's IGCSE 0620 February March 2024, and the paper is 0620. Okay, let's start with question number 1. Calcium carbonate is an insoluble solid. Okay, calcium carbonate can be made by adding an excess aqueous calcium chloride to aqueous calcium carbonate. Okay. Yeah, just give me a minute, please. Okay. So here we have a equation by which calcium carbonate, which is water insoluble, made. So see, these are aqueous, this is aqueous, and it's a solid. So that's why the precipitates are formed, right? Because the solid is formed by the mixing of two aqueous solutions. The student make a sample of calcium carbonate. The first two steps of the method are shown in figure 1.1. Okay. So what is step 1? An excess of aqueous calcium chloride to aqueous sodium carbonate. Okay. So they are adding calcium chloride to sodium carbonate. Step 2, stir the mixture. So it is sodium carbonate and it is calcium chloride. Okay. Now what they are asking, name the item of apparatus labeled A in figure 1.1. Yes, what it is? Yes, can anyone know what it is?
A stirring rod?
Okay. But basically remember the thing which we use to stir a solution, that is called glass rod. We name it glass rod. Okay. So do remember this thing. It's a glass rod which is used to stir any solution in the chemistry lab. Now, so just why the mixture is stirred in step 2. Okay. So yes.
To allow the particles to react and collide with each other?
So basically, yeah, but that is a very, it's better. You are right, but it's better we mix to make them mix, basic. So they mix with each other. To mix with each other. Is this clear to all of you? Now, next part. After step 2, the student filtered the mixture to remove the solid calcium carbonate formed and collect the filtrate. Okay. Draw a label diagram to show the apparatus used for this filtration. Okay. So whenever you do have to filter something, what you really do, you are going to make a conical flask. Do remember this thing. Is this visible to you? So what you are going to do, you are going to make one conical flask. And then on the conical flask, on the opening of the conical flask, you are going to put a funnel like this. And then in the funnel by this, you can show the filter paper, and over here you are going to have a filtrate, the solid filtrate, and here you will get the filtrate, and on the top it's not, sorry, my bad, it's not filtrate, it's a residue. So now you need to label it. funnel, filtrate, conical flask,
Sir, it's
filter
not
paper.
visible.
Just give me a minute.
Yes, sir, now it's better.
Yes, is it visible now?
Yes, sir.
Okay. So conical flask, filter paper, funnel, and that solid. You can mark it as a residue, the precipitates, because the leftover thing is called residue and which pass through the filter paper is called filtrate. Is this clear to all of you? So these are the things that you need to label, okay? Any confusion?
No, sir.
Okay. Now, next. The solid calcium carbonate obtained by filtration is not pure. Okay. Identify one substance other than water which is mixed with the calcium carbonate and makes it impure. So, how to figure out this thing? The easiest way to figure out this thing is that what are your products? Your This is the solid and this is the aqueous sodium chloride. So there is a chance that it might contain some sodium chloride with it. So whenever they ask you that if it is not pure, so why it is impure and what other thing is present. So do remember when there are two products which are being formed, so it might be due to the other product which is formed. Okay. So over here, I'm going to answer it sodium chloride. Is this clear?
Yes.
Yes.
Yes, sir.
Now, describe how substance you have identified in D2 can be removed from the calcium carbonate. Yes, how can you remove it? Any suggestions?
The distillation.
How distillation? Because the that is a solid. From solid, so what you do, if it think sodium chloride is water soluble, isn't it? Yes. So if some of it's
Yes,
a
sir.
whole solid, and if there is some solid chloride, and if you put a water over here, so what water will do? Water is going to wash it as it is not dissolved. So water can move through and pass the filter paper. So along with water, it takes all the sodium chloride which is there. Along with water, it is passed and collected over here, and now it is only calcium carbonate. Is this understandable? Because see, they are saying that sodium chloride is aqueous. So it might contain if some traces, and then when we add water from the top, so what water is gonna do? Water is going to take that sodium chloride along with it into the conical flask, and now we are left with only calcium carbonate. Is this clear to all of you?
Yes, sir.
Okay. So pouring water on the residue in the funnel. So as a result, it gets washed away and the impurities can be removed. Now, next, describe a test the student can do on the filtrate to show that the calcium chloride used is in excess. Give the result the student obtains if calcium chloride is in excess. So if calcium chloride is in excess, it means some of the calcium chloride left behind, right? And if that calcium chloride left behind, and if you see that calcium chloride is aqueous, right? Is aqueous. So that calcium chloride must be present in the filtrate, right? Is this understandable? Yes, is this?
Yes.
Okay. So if calcium chloride is there, so it means calcium chloride has a calcium ions in it. So the solution contains calcium ions, right? Is this understandable? To if the filtrate has calcium ions present in it, then it means it do contain calcium chloride. Is this point is understandable to all of you?
Yes. Yes.
Okay. So what is the test for calcium ions? As I have told you, they provide you this. So see, effect of sodium hydroxide on calcium ion. White precipitates insoluble in excess. So what I'm going to write, I'm going to add aqueous sodium hydroxide, right? And then what I'm going to do, I'm going to get a white precipitates if calcium is there. And that when I add more, so aqueous sodium hydroxide, the white precipitate remains insoluble. So add aqueous sodium hydroxide, right?
Yes.
The results would be white precipitates and remains insoluble on adding excess aqueous sodium hydroxide. I hope it's understandable to all of you. Now, question number 2. So for such questions, you need to be, very vigilant and very focused. Because if you collect the information and gather that information and keep it along while attempting the questions which are asked after these information, so it will be very helpful. And if you do not able to retain or understand this information which is provided in this region, then you are not going to attempt the rest of the part. So you have to be understand this very carefully. Okay. So a student investigates the reaction between aqueous sodium carbonate and two different solutions of dilute hydrochloric acid labeled A and B. The student does 3 experiments, okay. So in experiment 1, rinse a burette with the distilled water and then with dilute hydrochloric acid A. Rinse a conical flask with distilled water. Fill the burette with dilute hydrochloric acid A. So see, burette has been rinsed with hydrochloric acid A, and that's why it is filled with hydrochloric acid A. Now, run some of the dilute hydrochloric acid out of the burette so that the level of the hydrochloric acid is on the burette scale. Okay. Record the initial burette reading. Use measuring cylinder to pour 25 centimeter cube of aqueous sodium carbonate into conical flask. Add 5 drops of methyl orange indicator to the conical flask. Stand the conical flask on a white tile. Slowly add dilute hydrochloric acid A from burette to the conical flask while swirling the flask until the solution becomes orange. Record the final burette reading. I hope you have understood the method. Now in experiment 2, refill the burette with dilute hydrochloric acid A. So again in experiment A, hydrochloric acid is used. Some of the dilute hydrochloric acid out of the burette so that, okay, so make it on a scale. Record the initial burette reading. Empty the conical flask, transfer it with distilled water. Use the measuring cylinder to pour 25 centimeter of sodium carbonate into the flask. Add 5 drops of thymolphthalein indicator to the conical flask. So what is the difference between the two experiments? They just do the same method, but they use the different indicator, right? Stand the conical flask on the white tile. Slowly add dilute hydrochloric acid A from the burette to the conical flask while swirling the flask. Record the final burette reading. So, is there any error in experiment 1 and 2? Yes?
So in experiment 1 and 2, like we use different indicators.
No, I am asking, is there any error?
No.
Do you guys know how to do the titration?
Sir, shouldn't we use a pipette instead of burette?
No. Actually, yeah, there is a small error that instead of measuring flask, where they have used the measuring cylinder over here, they need to use pipette for accurate results. Is this understandable?
Yes, sir.
Okay. Now, what happens next? Repeat in experiment 3. Repeat experiment with using hydrochloric acid B instead of, okay. So in experiment 3, there is a difference with the experiment A using a different hydrochloric acid, but the same indicator has been used. Okay. Now let's move to the questions. Use the burette diagrams in figure 2.1, 2.2, 2.3. Record the readings of the experiment 1, 2, and 3 in table 2.1 and complete table 2.1. Okay. So for experiment 1, if you see the final reading, can anyone tell me what is the final reading?
26.2.
And the initial reading is
0.8.
0.8. Yeah, 26.2 and 0.8. So 26.2 is the final reading and 0.8 is the initial reading, right? For experiment 2, initial reading is 0.2, final reading is 12.9, isn't it? So 0.2 is the initial and the final is 12.9. Then initial is 1.0 and it's 39.1. Okay. Now to calculate the volume of hydrochloric acid, because hydrochloric acid was in burette, so we take the difference of these values to get uh, the volume of hydrochloric acid used. So in the first case, 26.2 minus 0.8,
25.4,
25.4. In the second case,
12.7,
sorry,
12.7,
12.7. And in the third one,
38.1.
38.1. I hope till here it's clear to all of you.
Yes, sir.
Okay. Now, next, state which solution of dilute hydrochloric acid A or B is more concentrated. Explain your answer. So the one having a more concentrated, first try to understand this term, means having a more moles in the same volume, right?
Yes.
So it means with this, so if it has a more volume, more moles of HCl in same volume, so if it has a more moles in the same volume, so how much volume of this concentrated acid is going to be used up? The more greater, the larger volume or the smaller volume?
The smaller volume.
The smaller volume. Very good. So you need to understand this because there are more moles in the same volume, the concentrated one. So it means as it has a more moles, so it is going to neutralize quickly or neutralize with a small volume. So if you see in experiment 1 and experiment 3, in experiment 1 we have HClA, in experiment 3 we have HClB, in experiment 2 we have again HClA, right? But the indicators are different. So see, HClA and HClB, HClA needs only 25.4 volume has been used, and for HClB it's 38.1 centimeter cube of volume has been used. So the lesser volume of HCl is used, HClA is used, so it means HClA is the concentrated one. So I'm going to mention A, and then in explanation I'm going to write as its volume used is lesser. Is this clear to all of you?
Yes, sir.
Okay. Now, deduce how many times more concentrated this solution of dilute hydrochloric acid is than the other solution of dilute hydrochloric acid. So it's easy that how much more concentrated it is, we have their volume, so you can take the ratio of their volumes to identify it. So it's 38.1 over 25.4. Can anyone divide it and tell me what is the ratio?
1.5.
1.5, right? So,
Why did you divide?
hmm?
Why did you
Yes,
divide?
because on dividing we get the ratio of their volumes, isn't it? See, on simplifying, isn't it? It is 1.5 over 1. Right? Yes, is this point is clear or not?
Yes.
Now see, this is the ratio of what? Volume. That it is HClB and it is HClA. So it helps me to figure out that 1.5 more volume times more volume is used, isn't it?
Yes, sir.
So if it's 1.5 times more volume is used, so it clearly indicates that this one is 1.5 times more concentrated. Is this understandable? Yes?
Yes, sir.
Yes, if any one of you has any confusion in it, please ask.
Sir, why won't we use 12.7?
12.7 is a same HClA with a different indicator, isn't it?
Okay, okay. Got it.
I hope it's clear to all of you. Now, compare the volume of dilute hydrochloric acid A used in experiment 1 to the volume of dilute hydrochloric acid A in experiment 2. So, see, in experiment 1 and experiment 2, both we have used the same hydrochloric acid. So, they are asking to compare the volumes. So, in experiment 1, dilute hydrochloric acid used was 24.4 centimeter cube. And in experiment 2, the dilute hydrochloric acid used is 12.7 centimeter cube. So now you divide these to identify how much more volume is used. So isn't it? Isn't it? It's 2. Right?
Yes, sir.
So our comparison will be that volume of hydrochloric acid A in experiment 1 is more actually twice of volume of HClA used in experiment 2. Is this clear to all of you? Now, what they are asking, deduce the volume of dilute hydrochloric acid be required to reach the end point if experiment 3 is repeating using thymolphene indicator instead of methyl orange indicator. Use your answer to C1 to help. So see, now see this. Let me write. Over here, it's a HClA, and over here, it's a HClA. But the difference is over here, it's a methyl orange indicator, and over here, it's a thymolphthalein indicator, right? Over here, it's a HClB with the methyl orange indicator, right? So if see the ratio, it is actually they exist in a 2:1 ratio, isn't it? The same HCl with the different indicators, their volume ratio is exactly 1:2 or 2:1, isn't it? Is this understandable?
Yes.
So if
Yes, sir.
instead of methyl orange, I use thymolphene with HClB. So I'm going to get exactly half of this volume. So can anyone do the half of this volume? It is going to be 19 plus 19, 18, right? Oh, sorry, 38. So 19.05,
Zero
half
five.
of this one.
Yes,
Yeah.
sir.
So we are going to just show 38.01 over to, sorry, 38.1. So 19.05. And then centimeter cube as well, because they haven't mentioned the unit. Is this clear?
Sir, what could be the reason in such a different reading of volumes using different indicators?
See, they haven't mentioned anything about that, but most of the time, sometimes that it happens that that indicator is also taking part in the reaction. So if the indicator is also reacting and are also undergoing acid-base reaction, so what is going to happen? Not only just acid, the indicator is also, for example, using up the base. So as a result, less volume of acid is going to be used because the rest of the base is actually neutralized by the indicator.
I see, sir. Thank you.
Yeah, but that's what examiner, if they ask you a reasoning like this, so they gave you some hint, they gave you some information about that and then ask you.
Okay.
Okay. Now, D part. At the start of experiment 3, the burette is rinsed with distilled water and then with the dilute hydrochloric acid B. Identify the substance removed from the burette when it is rinsed with distilled water at the start of experiment 3. So, before experiment 3, in the burette, what we were using? We were using hydrochloric acid A, right?
Yes.
So that's why we are rinsing the water to remove hydrochloric acid A. Describe how the results of the titration would change if burette was not rinsed with dilute hydrochloric acid B and after it had been rinsed with water. Okay, first tell me, did you guys understand this part?
Yes, sir.
Okay, so if you rinse it with water and then you forgot to rinse with HCl, so the burette contains water in it, and before rinsing it with the HCl, you just added the HCl in it. So that HCl gets diluted because of the water present in it. So when it gets diluted, now a greater volume is going to be used up from the burette. Is this understandable?
Yes, sir.
A larger volume of acid is needed. Now, next, explain why the conical flask is not rinsed with aqueous sodium carbonate after it is rinsed with water. Yes, can anyone tell me? See, are we measuring anything in the conical flask?
No.
No, right? Because one thing is being measured in the burette and the other thing was measured in the pipette. And then we are transferring both of them, one thing earlier in the flask and then the other thing. If I rinse it with the aqueous sodium carbonate, for example, before adding it, so it already contains sodium carbonate in it. And then if I am adding mm, a measured sodium carbonate from the burette to it, so from the pipette to the flask, so the flask has a greater volume than what we need. It increases the volume of sodium carbonate that we are using. We are expecting and we are supposed to use 25 centimeter cube, for example, and burette is going to give me the exact 25 centimeter cube of volume. So I'm measuring the 25 centimeter cube of volume from the pipette, okay? And I'm going to transfer it in the conical flask. But if the conical flask is already being rinsed with sodium carbonate, so it has some sodium carbonate in it, right? And I measured the exact 25 centimeter cube of sodium carbonate in the pipette and added in the flask. So flask already had some of it, and I have exactly added 25 centimeter cube. So it increases the volume of sodium carbonate. Is this understandable? The result, the volume of sodium carbonate is increased. Yes, is this clear to all of you?
Yes, sir.
Okay. Now, next part. Explain why white tile is used during the titration.
To see the color change more clearly.
Very good, to see the color change clearly. So the color change would be visible, more visible. Is this clear? Now, describe the effect on result of forming the aqueous sodium carbonate used in experiment 1. Before carrying out titration, explain your answer. So sodium carbonate is a group 1 carbonate, right? And
Yes.
there is no reaction of heating it. So there is going to be no effect, as no change in volume or moles of sodium carbonate. Is this understandable to all of you?
So why will be there no effect?
Hmm?
Why will there be no effect?
Because let me show you. If you heat calcium carbonate, what happens? It decomposes to give you this, right? It's a group 2. But it's a sodium carbonate, which is from group 1, right?
Yes.
So if I'm going to heat it, no effect, because there is a strong bonds. It's actually the property of group 1 carbonates. Group 1 carbonates, they are very strong bonds and thermally stable, which means they resist the heat. Is this understandable?
Yes, sir.
Okay, now question number 3. A student tests two substances, solid C and solid D. Test on solid C. Solid C is ammonium iodide. Okay, so they have told you what is solid C. Solid C is ammonium iodide. The student dissolves solid C in water to form solution C. The student divides solution C into 3 approximately equal portions. Complete the expected observation. To the first portion of solution C, the student adds about 1 centimeter cube of dilute nitric acid followed by few drops of aqueous barium nitrate. Okay. What will be the observation? So what we are adding barium nitrate, right? And what we have ammonium iodide, right? So if you look over here, what you have added, we have a iodide and we have ammonium. For ammonium, we are going to use sodium hydroxide, and on warming, it will give you ammonia. So iodide, acidified with dilute nitric acid, and then silver nitrate. Okay. So it means that for iodide, we are not going to add barium, right? Not with nor with ammonium ion. So it means over here, the observation would be no change. Is this clear to all of you? Because
Yes, sir.
adding barium nitrate would not give the test with either ammonium or with iodide. Now, to the second portion of solution C, the student adds 1 centimeter cube of dilute nitric acid followed by a few drops of aqueous silver nitrate. So we have just seen that when there is an iodide, and you add silver nitrate, what you are going to get? You are going to get yellow precipitate. Now, next part. To the third portion of solution C, the student adds an excess of aqueous sodium hydroxide observation. So with sodium hydroxide, no change, because see, they have mentioned that ammonia produced on warming, right? So again, you are going to write no change. The student warms the product from C1 and test any gas. So, okay, on warming, gas form. Now you are going to write that test for the gas. So the test, so they have mentioned that ammonia is being formed. So what is the test for ammonia? That it turns damp red litmus paper blue. So you are going to write both the things over here as they have mentioned, write the test as well. So gas form turns damp red litmus paper blue. Now, test on solution B. Table 3.1 shows the test and the student's observation. Do a flame test on solid D, yellow colored flame. So C, if you are getting the yellow colored flame, so it is hinting you that it might contain sodium ion in it, right? So from this, what I have concluded, that there might be a sodium ion. Now, gentle heating about half of the remaining solution, solid D. Hold a strip of anhydrous cobalt to chloride paper at the mouth of the boiling tube. Steam is given off and condensation forms at the top of the boiling tube. The anhydrous cobalt to chloride paper changes color. What does this mean? Yes. Isn't it? It means water was there.
Yes.
So it means that there is a water of crystallization in compound D. So do compound D contains actually XH2O. We don't know how many water are there, but this helps because On heating C, they said that steam is formed, and that steam, when reaches to the mouth, it condenses, and the cobalt 2 chloride changes its color, which indicates that there is a water. Is this understandable to all of you? Now,
Yes, sir.
okay. Next, dissolve the remaining solution D in water to form solid D in water to form solution D. Divide solution D into three portions. The first portion of solution D, add aqueous ammonia few drops until in excess green precipitates, which is insoluble in excess. So if green precipitates are formed and which are insoluble in excess, so it might has two chances, either if it's Fe2 positive or it's chromium 3 positive. You can check it from here. See, aqueous ammonia, chromium 3, Fe2. Green precipitates insoluble in excess, right? Now, to the second portion of solution D, add a piece of aluminum foil and about 5 centimeter cube of aqueous sodium hydroxide. Okay. Yeah, sodium hydroxide will give you the green precipitate. Heat the mixture formed and hold damp red litmus paper at the mouth of the boiling tube. The red litmus paper remain red. So on heating, if you see, so it means it doesn't contain nitrate ion, because that is the test for nitrate ion. If you see over here, aqueous sodium hydroxide, aluminum foil, warm carefully, ammonia produced. So ammonia turns red litmus blue, the red litmus stays red. So it means no ammonia is produced and no nitrate ion. So no nitrate ion. Okay, green precipitate are there. So it means if it might have a greater chance with sodium hydroxide if I am getting green precipitate. So it might be Fe2 positive, because chromium precipitate dissolves in excess and we are adding 5 centimeter cube, right? So if you see chromium soluble in excess, right? But over here it is written green precipitate. They haven't mentioned that it is being dissolved. So it might has a chance that we have iron 2 positive ion. Yeah, it is iron 2 positive. That's what I think. Now, next. To the third portion of the solution, we add about 5 centimeter cube of diluted acid effervescence. So on adding acid, if you are getting the effervescence, so that effervescence is due to carbon dioxide gas, and it means D must contain a carbonate ion bubble. Any gas formed through a lime water, the lime water terms will be. So see, it's the indication. Now, what are their questions? State the final color of the cobalt 2 chloride. So cobalt 2 chloride is blue, and with the absorbing water, when in contact in water, it turns pink. So the final color is pink. Next, state what ion are present in test 4. State what ion the observation test 4 show is not present. So what we have identified, that nitrate is not present, no nitrates, right? So nitrate is not present. Identify the gas produced in test 5. So we have identified its carbon dioxide. Identify the 3 ions present in solid B. So the yellow flame tells us that it has ammonia. From here, we have concluded it's iron 2 positive, and from here we have concluded that it's carbonate. So it contains sodium ion, iron 2 positive ion, and carbonate ion. I hope it's clear to all of you.
Yes,
Yes,
sir.
that's clear.
Okay. Now, next. Okay, 6-mark question. Now, what they are saying, when excess of dilute sulfuric acid is added to a solid zinc, hydrogen gas and hydrogen sulfate are formed. Okay, you got the equation. Plan an experiment to show that copper is a catalyst for this reaction. Your plan should include how the results of experiment will show that copper is a catalyst for this reaction. You are provided with zinc water, dilute sulfuric acid, copper powder, and common laboratory apparatus. So, okay, so it means we have to plan 2 experiments, one with the copper and one without a copper. We are going to mix sulfuric acid and zinc in the presence of copper, and then without the copper, right? So see how you are going to format these type of equation. You are going to specify that we are going to use the fixed volume. So for example, first, okay, and in this reaction, a gas is being formed, right? So we are going to measure the volume of the gas per unit time, that in how much time, how much volume of gas is formed. Or for example, we set the time that, for example, we are going to measure the take count, wait for the 5 minutes, and then after 5 minutes, we are going to see how much gas is formed, right? So use fixed volume of sulfuric acid and transfer it in container. Now add fixed mass of zinc and start timer. Is this understandable?
Yes, sir.
Yeah, I think it's better to write, either you can use beaker or conical flask. Okay. Now record the time till gas stop forming. Is this understandable? Yes. Till
Yes.
it. Okay.
Yes, sir.
Now repeat the experiment, but add recorded add copper before zinc and record the mass of copper.
So why are we adding copper before zinc?
Because zinc and sulfuric acid are reactant. So if you add zinc earlier, so the reaction has been already started.
Okay, got it.
The catalyst must be present before both the reactants interact with each other, right?
Okay.
Okay. Again, you are going to record that time till gas stop forming, which is lower, which is lesser, shows copper acting as a catalyst. Is this understandable? Further, you can assure this. Remove copper by filtration. Record its mass again. Showing no change in mass indicates copper as a catalyst, as catalyst does not react. So their mass remains same. Is this understandable to all of you?
Sir, why is the gas produced less?
Because we are adding zinc, the same reaction is taking place, isn't it?
Yes.
See, this reaction is occurring once without copper and secondly with copper. So with the copper, again, the gas would form. Now the gas would form more quickly, and these two turning into this more quickly. They will going to turn into the products in the lesser time. So for example, the time that till the gas stop forming is 5 minutes over here, for example. But when we have added a catalyst, now it is lesser. For example, we are getting now, let's say 3 minutes. And then when we filter
Okay.
the copper, we have weighed it, and it shows that, as you know, that the catalyst does not react. So its mass is same as it was before mixing it, right?
Yes.
So is this clear to all of you?
Yes.
Sir.
Okay. So we are done with one paper. Now tomorrow we are going to do a 5070 ATP paper. And then the day after tomorrow, we are again going to do 0620. So one IGCSE and one O levels, okay? So see you everyone tomorrow, inshallah, same timing. Till then, take care. Goodbye. And Allah Hafiz.
Assalamualaikum, sir.
Allah Hafiz, sir.
Namaste.